Hi. So I'm Louis, I'm a dev tech at NVIDIA, and I was very lucky to be able to work with Johan Andersson from DICE on the SSAO in Battlefield 3, the HBAO in particular. This talk is about how we stabilized the SSAO using selective temporal filtering. So briefly, I assume most of you are familiar with SSAO. I just want to do a quick recap. According to me, it has become now the de facto approach for rendering AO on dynamic scenes in games with no pre-computation. The basic idea is to use the scene depth buffer as an approximation of the scene geometry. And there are various ways of using that depth information. I won't go in detail here, but here are some references if you're more interested. HBAO is a type of SSAO algorithm that considers the depth buffer as a height field and approximates the result of ray tracing this height field in image space. I'd like to mention that since the original HBAO algorithm from SIGGRAPH 2008 and ShaderX7, we improved the sampling so that we take a finer step at the center of the kernel, and that gives higher detail, it reduces halos, and that's the version that was used in Battlefield 3. If you want that implementation, you can check the NVIDIA SDK SSAO 11 sample. So HBAO was used in Battlefield 3 for the high and ultra graphics quality presets. Here's how it looks. That's actually a screenshot from Johan Andersson's talk from SIGGRAPH 2010. And the original HBAO pipeline in Frostbite 2, before we added the temporal stuff, looked like this. It takes as input view depth in full res, downsamples that to half resolution. Then it renders HBAO in half resolution as well, using up to 18 samples per pixel. And the half resolution AO is then upsampled back to full resolution. The depth, full resolution depth, is packed together with the AO in a 2-channel FP16 texture, which is then blurred horizontally and vertically using an edge-preserving filter. This is quite standard now for SSAO in games. It takes 2.5 milliseconds overall on GTX 560 Ti in 19:12 resolution. One thing I'd like to mention here is that in Frostbite, the SSAO is multiplied over the whole shaded color. So it's multiplied over everything, including the diffuse and specular, everything. And that actually worked quite well. It gave a specific look that looked quite good. Here's a screenshot with HBAO. So it has a lot of grass. And the HBAO only on that scene. So here, you see that the HBAO adds darkness to the grass in a plausible way. And if I switch back between, you can see that the occlusion from the AO is helping to make the grass feel more like it's grounded to the ground. It's more realistic. Now, while this looked pretty good on screenshots, we had the problem that it didn't look good in motion. So here's how it looked in motion. Let's restart. We had massive flickering on the grass, and any thin object in the game actually had this massive flickering. It was not acceptable. We had to fix that somehow. So we fixed this by using temporal filtering, as I mentioned. But we had hard constraints. The easy part was we only had to support PC because there is no HBAO in Frostbite 2 for other platforms. But we had to make it very fast because it was already 2.5 milliseconds. We wanted to make it even faster if possible. We couldn't go much higher than 2.5 milliseconds in 19:12. And it had to be very high quality as well because it was going to be used for the high and ultra graphics quality presets. We considered doing the SSAO in full res or dual res using a mix of half res and full res, but that would have been too expensive, and it may have remained some flickering it was not guaranteed to fix everything. We could also have just masked out the SSAO or brightened the SSAO. Sorry, slides are not showing anymore. This actually sucks. Okay, so what do I do now? I'm going to try this. Yeah, the problem is I've got videos and... Oh, yeah. So is it working now? Oh, yeah, fine. So, yeah, we could also have just brightened the SSAO on the problematic objects or just masked it out. But we wanted to keep full strength SSAO on everything. And as I showed earlier, the grass in particular was benefiting from SSAO. We wanted to keep on everything. So we went for this temporal filtering approach. And it makes sense because by definition, the AO does not depend on the scene geometry. It only depends on the camera. So for static or nearly static geometry, we can reproject the AO from the previous frame into the current frame and interpolate the previous AO with the current AO to reduce the variance between frames. That's the basic idea of temporal filtering. And it has been used successfully in the past in Gears of War 2, for example. Okay. Sorry about that. Yeah, I think I have serious problems. So, I don't know. Okay. All right. So we start from the current camera, from a given pixel, and unproject that pixel to world space based on the UV and the Z, and then project that position to the previous camera, which gets us a UV value in the previous camera space. And then unproject that again to world space. So now we have two world space positions for the same original point. And if those two positions are more or less the same, that means that the point didn't move too much between frames and it was available in the previous frame, then we can reuse the AO value from the previous frame. That's the basic idea of reverse reprojection from the Neab et al. 2007. On top of that, we adapted this temporal refinement idea from Matos et al., which says that if the point didn't move too much between frames, then we can essentially compute a rolling average over multiple frames. To do that, we just need to fetch the previous AO, fetch the number of frames that have been accumulated so far in the solution, which is ni-1 here. And each frame, we increment that number of frames by 1, and we clamp it to maximum value. We used 8. So we keep the rolling average going. We keep filtering the AO. It never fully converges. Now, if the point was not available in the previous frame, so we could not reproject, then we just discard the previous AO value and restart the filter to 1. We use the disocclusion test from Matos et al. Again, which says that the 2 points are similar if they have similar view space depth in the previous frame. And there is an epsilon threshold here, which is the maximum relative depth delta. Now, to support dynamic objects, actually nearly static objects, such as the waving grass that doesn't move too much, all we had to do was to relax this test by just using a large threshold. So we used actually 10%, so that we could still reproject the points that are moving a little bit like the grass and still get some temporal filtering on those. This actually worked very well, and it was very simple. We didn't have to track the motion. So, challenge. I've got a video. All right. So here is how it looks with a very tiny epsilon. In this scene, you can see that the grass is highly flickering, like before. And here's what would happen if we had a very large epsilon, meaning we have no disocclusion test. We reproject everything. So in that case, you saw that there was no flickering, but now we have these weird ghosting artifacts on the bush here, as you saw. The ghosting artifacts happen, they happen here on the background of this scene because these background pixels were not available in the previous frame. They were occluded. And all of a sudden, they became visible on screen. And there was no previous frame information for those. So, whoa. Wow, that's really advanced. Oh, yeah, okay. Great. So, last, with the 10% epsilon threshold now, we had the benefit of both. We could fix the flickering, and we didn't have any ghosting artifacts. So, I'm going to try to show that video. Okay, so now you see that the grass is all smooth and stable, and there is no ghosting going on for the disoccluded pixels. Okay. However, we found this additional problem, which were trailing artifacts below the character. And those were due to the fact that we were interpolating the AO on the static objects, but the AO was produced by dynamic objects. So that's actually a known issue in reprojection in general. So these artifacts look like those. They were quite funny, and yeah, we didn't like them too much, so we wanted to fix them with no profit. We didn't want to have any additional cost for that, so we just wanted to find a cheap solution. And we observed that with the temporal filter disabled, we didn't have the trailing problem, but we had these flickering pixels on foliage, mostly on foliage, and the other pixels, such as the ground here, didn't have any flickering. So we didn't need temporal filtering on the ground. We just needed the temporal filtering on foliage. However, with the temporal filter enabled, we had these trailing artifacts. So the idea was to assume that the flickering pixels and the trailing pixels were mutually exclusive sets of pixels. So we could classify the screen as either being potentially trailing or potentially flickering. And then we would just disable the temporal filter on the stable pixels. To do that, we started from the normal reconstruction, from the SSAO shader. That's basic normal reconstruction. And the idea is that if this normal was noisy, then most likely the SSAO was going to be noisy at that pixel. So we tried to derive a classification algorithm based on the quantities from this normal reconstruction. And we did so by fetching the nearest pixels to the center. So here's a 1D example. We fetch the pixels to the left, to the right, convert that to view depth, and we select the nearest point to the center point. Then we just classify the pixel as continuous if the distance to the nearest point is less than a given threshold in view space. It's very simple. Here are some examples. So there's this weird case in the middle where the left part is continuous and the right part is discontinuous. In that case, we just classify it as piecewise continuous. And overall, we just had 2 half-resolution passes for the whole classification. The first pass is to compute the continuity mask based on the nearest neighbors. The second pass is to stabilize the mask. We use the dilation pass with the 4x4 kernel. Here's an example scene and the stability classification here. So the black pixels mean unstable, and the white means stable. As you can see, the grass and the trees have a lot of unstable pixels, which makes sense. But in the background, we had essentially all the pixels were black. And that's actually an algorithmic issue due to the fact that we used the view space threshold. And that actually worked fine for us. That meant that all of the background pixels were classified as potential trailing. That was fine because there was no visible trailing in the background. Then second pass is the dilation pass, which essentially stabilizes the mask by dilating the unstable pixels. At the end, a pixel is classified as discontinuous if it has at least one discontinuity in its 4x4 neighborhood. Overall, the filter was enabled only for the pixels that were classified as unstable and did not have any disocclusion. Okay. So here's a video of the final result with this classification and selective temporal filtering. As you can see, the grass is now highly stable. And there was still a bit of flickering in the background, but that turned out to not be an issue. Now, if we move to the second test case here, and we look at the ground, there is no trailing artifact below the character. So that's how we fixed it. Now, with the colors, the final rendering looked like this. The grass was looking quite stable. And yeah, we were quite happy with this result. So the only change, the two changes that we made were we added this half-res mask dilation path that actually took 0.05 milliseconds in this 19x12 test. And we added the temporal reprojection stuff at the end of the final blur pass, which added a 0.4 millisecond cost. And we used MRTs to output the information to the history buffers. All right, so yeah, overall the performance hit was only 1.6%. So we went from 25.2 milliseconds from 25.6 milliseconds in this test case. Now the drawback of the technique is that it has to store history information in history buffers. It has to store the previous AO, the previous Z, the previous number of frames accumulated so far. So we stored those in full resolution 1x MSA buffers. For multi-GPU rendering, we used we simply created one set of buffer per GPU and alternated between them. And we also duplicated the state per GPU. So each GPU had its own buffers and its own state. And we cleared the buffers on first use. Here's for reference, full listing of the selective temporal filtering algorithm. That's an optimized version. I just would like to mention that we used clamp to border for fetching the depth, so that the depth outside of the screen was invalid. And for fetching the EO, we used bilinear filtering. Now, I'd like to mention a blur optimization that we also added and gave us an extra speed up. So here's the HBAO with no filtering at all. No blur, no selective temporal filtering at all. It looks quite noisy, as you can see. And now with the blur enabled and the selective temporal filter enabled, it looks like this. So the blur that we do is, as I mentioned, two 1D kernels, a first horizontal pass, then a vertical pass. It takes as input the half resolution AO and the full resolution non-MSA depth. And it's just a basic cross-bilateral filter, which is a Gaussian blur with depth-dependent weights. We looked at the Gaussian curve of that filter, and we noticed that actually, half of the samples were contributing 1/3 of the total weight. So we wanted to spend less time on those less important samples. And we did that by by replacing pairs of samples within between samples in the outer part of the kernel and doing bilinear taps in between samples, which is an approximation, but turned out to work very well. Here's again another view of that. So before we were doing point taps for each of the pixels in the kernel. And now we are doing point taps in the inner part of the kernel. But in the outer part, we do bilinear taps with a step size equal to 2. So here's how the brute force blur looks like. Here the horizontal pass takes 0.8 milliseconds. And here's how the adaptive sampling looks like. You probably cannot see the difference, but there is a tiny bit of difference. That gave us a 29% speed up on the horizontal pass, but only a 5% speed up on the vertical pass because we were doing the selective temporal filter there, so there was a lot more math. It was a lot more math limited. To sum up, I've presented two techniques that were used in the shipping game Battlefield 3 on PC. Generic fix for fixing flickering in SSAO with the low per fit, and an approximate cross bilateral filter using mix of point and bilinear taps. Thank you for your attention, and I'll be happy to answer questions on the HBAO in Battlefield 3.